Good afternoon, everyone. My name is Shangquan Sun. It's a great pleasure to be here at CVPR 2025 to present our work titled Semi-Supervised State Space Model with Dynamic Stacking Filter for Real-World Video Deraining. Thank you so much for joining me today. Video deraining focuses on removing rain streaks passing through camera. The existing learning-based deraining works rely heavily on synthetic datasets consisting of simulated rain patterns. The simulated rain patterns either come from the rain layers captured by Columbia University's CAVE lab or the automatic simulation of Adobe effects. The two ways make the synthetic rain streaks either lack temporal consistency or pattern diversity. Therefore, the simulated rain streaks are highly distinct from the real-world ones. As a result, the existing video deraining methods cannot generalize well on the real-world rainy videos. A good restoration model is expected to both enhance visual results and also improve the downstream vision model in degraded environment. However, there lacks a benchmark of downstream tasks like object detection and tracking under raining conditions. To benefit video deraining tasks, we get the inspiration from the image stacks concept from photography. Here shows an example of min stacks. With a single image, the details may be full of noise. However, if we take multiple images, align them, and then apply pixel-wise min filter to them, the noise will be significantly reduced. Here shows another example of median stacks. We want to only retain the background of a beautiful scene. However, there are some pedestrians sometimes, for example, in the foreground. In this case, we can take multiple images in different time and apply median filter to them to the aligned images. Because the moving objects will pass through the camera, the foreground will be removed. We then realized that the image stacking technique is quite useful in video deraining. Because rain streaks are bright and moving, the min and median filters will remove them. For the noise caused by rain patterns, min filter will remove it. Regarding the empty pixels, when aligning neighboring frames, the max filter will fill in the empty edges. To this end, we propose a dynamic stacking filter, DSF, able to simulate each of stack strategy to adaptively fuse the aligned video frames. Our work has three contributions, one for the DSF, the second for a video deraining member to propose, and the last is a benchmark for raining condition object detection and tracking. Since the min, max, median filter are indifferentiable, we find their approximate formats and design the DSF. For the brevity, we directly show the format of our dynamic stacking filter with two learnable parameters, A and B. By making the two parameters approach different values, the function can approximate the stack of different strategies. Then we will present our VD member, a semi-supervised video deraining state space model. To align neighboring frames, we firstly need to learn optical flow. To this end, we leverage a pre-trained light flow net to transfer optical flow knowledge to VD member. By predicting multi-frame optical flow, we can warp neighboring frames to the centering frame in one go. Then we input the original frames and also the aligned frames into the second VD member to restore the centering frame. Our VD member consists of two branches, one for spatial feature extraction and the other for temporal feature fusion. The intermediate features of spatial branch will be fused into temporal branch at each stage. The VD member consists of two vital modules, namely spatial state space model layer and temporal state space model layer. For the first module, we design a three-branch structure and leverage point-wise convolution layer and 5x5 depth-wise layer to extract spatial features. For the temporal one, we use our proposed DSF filter to adaptively fuse the temporal features and the input spatial feature. To learn on unpaired real-world raining videos, we design a median stacking loss. By applying median filter to the aligned frames, we can obtain a pseudo-clean frame where the majority of rain is removed. However, many artifacts or errors are introduced when applying warping and alignment. So we introduce a mask to select those patches with sufficient fidelity and containing rain streaks. We train our model on real-world raining videos by learning from the pseudo-clean patches. At last, we present the benchmark for rainy day object detection and tracking. We select 57 long raining videos from YouTube with totally 10,000 frames. Then we label the frames and obtain 33,000 objects for detection and 400 unique objects for tracking. There are totally 14 classes in our dataset. We call it Raining Video Object Detection and Tracking Benchmark, in short, the RVDT. The table shows its statistics and the figures show its examples. The videos show the detection and tracking results on the video from it. Next, we will show the results of our work. Our model obtains a state-of-the-art performance on the existing datasets, including NTU rain, rain scene complex, and rain scene light. As shown in the figure from the left, our model performs best with the least runtime and model size. We also show three groups of visual results on the right-hand side. Here we show our results on real-world rain videos. From the two example frames, our model removes all the rain streaks, while the existing methods leave some rain streaks unremoved. Here shows the video results on real-world video deraining. The third column shows the results of ours. We also compare the deraining models on improving the object detection and tracking models on rainy days. The experiments are conducted on our RVDT. And the detection models are YOLO V3 and MEGA from CVPR 2020. One is a single image detector and the second is a video-based detector. The results show that our VD member improves the two downstream models by the largest gains. Here shows two visual examples of deraining and detection. We can see from the first example, only our model can help YOLO V3 to detect the bicycle, while the other models mislead the detector and get a wrong prediction of person. Our model can also enhance the confidence of correct detection, like the motorbike and car in these two cases. We also show deraining and tracking results here. The tracking model is GTR from CVPR 2022. The results show that our VD member improves the tracking model by the largest gains. The visual comparison shows that only our model can remove all the rain streaks and also help the GTR detector to detect the umbrella in this case. This concludes my presentation. Thank you all for your attention. If you have any questions, please feel free to email me at shangquansun@gmail.com. Thank you again, and have a good day.